Hello and welcome to another walkthrough. Now this time it will be Edexcel A2 level Pure Math
Paper 2,
June 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of times, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Now here's the paper. And I'm gonna hit the timer now. Okay, let's get started. Number 1, factorize completely. All right. Okay, so we can see that there is an x in every term. So I'm just gonna factorize x out first. So I'm gonna get 2x squared minus 24x plus 40. Seems like we can also pull 2 out. So I'm just gonna pull 2 out and I get x squared minus 12x plus 20. So if I were to factorize this manually, then I would do x and x because that's x squared there. Well, 20 comes from minus 5 minus 4. You don't get minus 12 there. So let's do minus 2 and minus 10. Yeah? And that's just done. So that's done for the first part, like a warm-up here, guys. Number 2. Find the integral of that, giving the answer in the simplest form. Okay, this is indefinite integration, so we need a constant c, but so we're going to get, so that's going to be x to the 5 over 5 minus, okay, so x to the power of 1/2, if we add that by 1, we get 3 over 2. 3 over 2, you got to times 2 over 3. It's like 6 divided by 3 over 2, you get 2 over 3, right? And that's going to be 4, right? Yeah. So, 3 cancels 6 is 2. So that's going to be 4x to the power of 3 over 2 minus 3x plus c. Yeah. And that's it, I think. Yep. So let's just end there. Number 3. Good warm-ups here. Okay, number 3, we have that equation. And we need to find the exact value of x over y. Right. Okay. Well, we could take log on both sides, but yeah, let's take log. Let's just do ln. So ln 3 to the x equals ln 7 to the y, and we can do x ln 3 equals y ln 7 here. Yeah. And then we have x over y, so I'm just going to do y divide down both sides and ln 7 divided by ln 3. Well, that's going to be, we can change that to, because look, I'm going to use this property here, where if you have log base k of b divided by log base k of a, you're going to, you are able to convert that to log base a of b. Yeah? So that's going to be log base 3 of 7, because ln is log base e. So in here the k would be the e, right? And I can just, 3 would become the base there, and 7 would become the argument. So that's the answer, I guess. Let me just double check my math here. Yeah, I think I'm happy with that. So that's the exact value. All right, good warm-ups here. Number 4. Okay, so number 4 here, the shape ABCD shown in figure 1 consists of a triangle ABD containing a sector ABC of a circle with center B. Okay, given that AD is 6.4, BD is 13, BA is 8, and BC is the same. So seems like BA and BC here is part of a sector, right? Yeah, it says so. So ABC is a sector with center B. All right. Show that the angle ABC is that radians to 3 significant figures. Right. Okay. So the radius is 8, and it gives you an arc or not? No. Okay, so let me think about that. Well, yeah, we can use cosine rule, sine rule, cosine rule, basically. Because we don't have any angle here, we should use cosine rule. So if we use cosine rule, we're going to get this angle, or yeah, we can use cosine rule for this angle, right? So part A, so let's say theta is angle ABC, yeah? So cos theta is going to be, right? Well, let me just plug in the whole equation, right? So I'm going to use this triangle where I find theta. Well, let me just draw that in the question. So this is theta basically, and that would be the A and the B, and this is the opposite, yeah? Okay, so 6.4 squared equals 8 squared plus 13 squared minus 2 times 8 times 13 cos theta. So theta equals arc cos, right? 8 squared plus 13 squared minus 6.4 squared divided by, yeah, 2 times 8 times 13. Okay, just rearranging everything and just making theta the subject. So we just plug in the calculator here, no problem. So arc cos, already in degree there. No, we want in radian, sorry. Radian, yep. Arc cos, fraction 8 squared plus 13 squared minus 6.4 squared, and then 2 times 8 times 13, close bracket. So that's 0.39429, blah blah blah. Gonna round that to 394, 3 significant figures. Okay, so there you go. Hang on. Yeah. So part B. Show that the angle ABC, wait, sorry, that's part A. Part B, the region R shown shaded in figure 1 is bounded by the line CD. Bounded by the line CD here. Okay, and the line DA, and yeah, it's already depicted in the diagram. Find the area R given the answer to that. Alright, so the shaded area here can be found by just finding the whole triangle area, and we're gonna take away the area of the sector, right? Yeah, that works. Alright, so area of R would be equal to the whole triangular area is half times, I'm gonna use again the legs being 13 and 8, and the angle between the legs is just the one we found in part A. So half times 8 times 13 times sine of the angle we found in part A, sine theta, which is this guy right here, 0.39429. Was it 29? Yep, that's fine. We're just going to carry more significant figures there for some precision. And then minus, right, the area of the sector being 1/2 times theta, which is 0.39429, times r squared, which is 8 squared. Yeah, that's it. We plug everything in, we get the answer. Alright, so 1/2 times 8 times 13 times sine, okay, I just need to plug that in again, 39429. 39429, yep, minus 1/2 times 0.39429 times 64, which is 8 squared. Let me check everything there. Yep, I think I'm happy with all that. So let's just write down the answer. 7.3 significant figures. Yep, 36 centimeters squared. Everything is in centimeters, so we are fine. Yep, so that is done for question 4. Question 5. Alright, the curve C has parametric equations that the point P with x coordinate minus 3 lies on the curve. Find the y coordinate of P, part A. Well, basically we just plug in minus 3 here to the x to find t and use that t to find y. Sounds good? So minus 3 equals t minus 1 over 2, yeah? And t is going to be minus 6 plus 1 equals minus 5, yeah? Okay? So we got t already here to be minus 5, and we're going to plug that to the y. Let me sip coffee. So y is going to be 5 times t plus 2 to the power of 4. That's going to be minus 4 to the power of 4. Yep. And minus 3 to the power of 4 is 81. 81 times 5 is 405. Yep, happy with that. That's the y coordinate of P. Part B. I'm just doing it again, just, when every time I do mental math, I need to be careful. Yeah, all right, yeah, I think that's fine. Part B, find a Cartesian equation for C, giving the answer in the form of that. All right, Cartesian equation, that is, well, let's see, if we make t the subject from x, and then we substitute in y, how about that? Yeah, that should work, right? So t equals 2x plus 1. That's from the x expression there, yeah? And then you sub it in the y, which is 5, in brackets t, now becomes 2x plus 1, plus 2 to the power of 4, yeah? So that would be 5, 2x plus 3 to the power of 4. Okay, and I think that's it. We don't need to expand. Yeah, Cartesian equation. Part C, hence or otherwise find the gradient of C at point P. Well, hence, right, probably best to follow the suggestion there. After we got the Cartesian, we're going to do dy by dx. I mean, you could have done parametric differentiation as well, but because we got the Cartesian anyway, so we're going to do a chain rule here of this one, because that's you have a polynomial there, like fx to the power of something, we can do chain rule. So bringing 4 down, we have 20, and the same thing to the power of the previous power minus 1, so we get 3 there. And don't forget to do the chain rule in the brackets, which is 2. So that's going to give me 40 2x plus 3 to the power of 3. Well, we want the gradient at point P, right? So that is when x equals minus 3. So dy by dx, yeah, which is the gradient of C at point P, would be equal to 40, 2 times minus 3 plus 3 to the power of 3. 2 times minus 3 is minus 6. Minus 6 plus 3 is minus 3. It's basically 40 times minus 3 to the power of 3. So that's going to be 3 to the power of 3 is minus 27 times 40. That's minus 1080. Ooh, that's huge. Okay, gradient, very huge there, like hugely negative. Let me just double check. So starting from the Cartesian equation maybe. So 2x plus 1, yeah, I think I'm okay with that. And subbing in becomes 2x plus 3 to the power of 4. We differentiate, so we get 20 power minus 1. And then, yep. And then we plug x equals minus 3 in. Becomes 2 times minus 3 here. Just going to write brackets maybe, because it looks like an x sometimes. So minus 6, minus 3 to the power of 3, minus 27. Yeah, that should be fine. Yeah, so I'm just going to keep my answer as that. Next question, number 6. What do we have here? Part A, given that x is small and in radians, use small angle approximation for cos theta to show that blah, blah, blah. All right, so in small angle approximation, if you look in the formula sheet, right, cos theta is going to be approximated to 1 minus theta squared over 2. Yeah, and sine theta will be approximated to theta, tan theta as well, same thing. So we have these, yeah, in the formula sheet. You can open that too. And then, so that means 1 minus cos squared 2x would be approximated to 1 minus, well, again, cos is the whole of 1 minus, this is cos, so theta being 2x here, yeah, and then you got to square that as well. So I'm going to do 1 minus 2x squared divided by 2. that is just cos 2x, right, in here, in the whole lot here, in the brackets, and then we got to square that as well, right? Okay, so that's going to be equal to 1 minus, well, if you square that, so this is basically 4x squared divided by 2, so that's 2x squared, right? The whole thing there. So it's just 1 minus 2 times 1 times 2x squared, so that's 4x squared. And then you expand it, like you multiply the 2x squared with the 2x squared, you get plus 4x to the 4. Yeah, that's it. And then if you expand that all out, 1 will minus with 1, so it goes away. So you have 4x squared minus 4x to the 4. So that is as required, right? Yep. Part B, given that x is small in radians again, use the answer to part A, the small angle approximation for sine theta and tan theta, to show that this is approximately that. All right, so that's part B there. Okay, so we already got the cos squared there, so we just plug it in maybe. Okay, let's just copy down this first, and then just sub in everything at once. Yeah. So that's going to be approximated to 4x. It's 4x, yeah? 4x squared minus 4x to the 4 divided by, so sine of theta, theta being small, so that's just going to be x over 3 on that one, times, same thing. Yeah, we get the same thing for tan, right? Yep, okay. And then, yeah, so you just have to keep going with the simplification. So see that if we take x squared out, we get 4. How about take 4x squared out? We get 1 minus x squared, right? And then this is just x squared. And then we have multiplied 9 up here because there is a 3 and a 3 there. So the x squared cancel, we get 36, 1 minus x squared. Yeah? Oh, so they want that form, so fine. 36 minus 36x squared. A and B are constants to be found. Yeah, I think I found them. There you go. Okay, hence given that x is very small, again, deduce an approximate value for this. Yeah, giving you a reason for your answer. Hence, given that x is very small, x is very small. All right, so if x is very small, so x tends to 0, that means 36x squared will tend to 0. Therefore, 36 minus 36x squared will be equal to 0. Okay, will be about 0. Let's write approximate there. Okay, so it's 0 there. Sorry, not 0, 36. Because this one is 0. Yeah, and we still have the 36 there. All right. So 36 is the answer. The reason, I think we already write here. Because when x tends to a very small number, 36x squared will tend to 0. So that will tend to 36, yeah? Okay, that's enough. Number 7 here. Given that blah, 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 find the value of each of the constants a, b, c, and d. All right, so this is, well, you can do that by long division. I'm just going to multiply all out by, let's see if I need to do that. Hang on. We could divide the whole thing using long division, right? Or I think long division is better here, and you can't use short division like I did in the other papers, because short division only works when you divide by a linear factor, but this is a quadratic factor. So I'm going to do x squared minus 2x minus 3. So if you multiply the two divider here at the bottom, yeah, these two, you're going to get this, right? And then you're going to use that to be the divider and divide the whole thing here. So this is called the dividend, to be divided, yeah, by the divider, or jargons. Okay, the first divided into the first, you get 3x, right? And then you multiply the whole thing, 3x cubed minus 6x squared. Yeah, multiply that, minus 6x squared, and multiply that, you get minus 9x. Subtract, yeah, the first one cancels, this one minus 2x squared, yeah, you gotta subtract that, and this is plus 3x, yeah, minus 6 minus 9. You pull the last one down, and then you divide the first into the first again, so that gives me minus 2, so minus 2x squared, right, plus you multiply back, plus 4x plus 6, yeah, okay, and subtract the 2, you get minus x down here, and minus 17 down here. So that will be the remainder, because we can't divide anymore because the first one here has a higher degree compared to that first one. Okay, so that means the left hand side will all be equal to 3x minus 2 plus so we have minus x minus 17 divided by x plus 1 and then x minus 3. So we need to do partial fractions here to split these two into c and d, right? So I'm just going to do minus x minus 17 equals, well, if you imagine, right, you're going to write this separate c over x plus 1 plus d over x minus 3, and like that. Yeah, like that. It's like a setup of a partial fraction operation here. And you gotta divide, you gotta multiply this in all the term, to this term and to this term. Multiply all the term. Yeah, so the left side will just be left with minus x minus 17. C will be left with x minus 3. D will be left with x plus 1. Because the method I'm using here is just substituting the critical value. So the critical value here will be 3 for that brackets and minus 1 for that brackets. Just the one that makes the brackets equal 0. So we sub x equals 3 in. We get minus 20 here on the left side. Why do I use black? Hang on. Okay, so x equals 3. That's going to be minus 20 equals. So the c will go to 0 there, the c term. And then we have here for d. That means d equals minus 5, right? Yeah, minus 20 divided by 4. Okay, and then if we sub x equals minus 1 in, we get minus 1 is 1, 1, minus 17 is minus 16 equals. The d will go to 0. We have the c here. So minus 1 minus 4 is minus 4c here. Yeah, and then we get c to be 4. Okay. So therefore we get now every one of them. So a is 3, b is minus 2, c is 4, and d is minus 5. Yeah, okay, there we go. Yeah, I think I'm okay with that. So let's do the next one. Oh, look at that. Next one, we have a graph here. Let's see what we got. We have a function fx, which is a quartic function again. Just like the paper one, they also have a quartic function in paper one. If you haven't seen it, just go check out. Figure 2 shows a sketch of the curve C with equation y equals fx, of course. Given that C has a local maximum at x equals minus 4, local maximum x minus 1 over 4, sorry. Local maximum, yeah, so it must be that point. Show that a equals minus 4. So a is in part of the function here. It's just the coordinate of that. Okay, 4 marks here. So local maximum, right? Let me think. We probably have to differentiate and set that to 0 to solve for x and show that it's, because this is show, not verify, right? So we're going to have to differentiate, I guess. So part A, we find f dash x first. So that's going to be differentiating each term here, 4x cubed plus, bringing 3 down, we get 1, so that's x squared minus 16x, yeah, plus a, yeah, and 17 over 3 goes away. And then we set this to 0 because it's a maximum point, yeah, and well, yeah, okay, this is fine. Yeah, we set this to 0, and then local maximum at x equals minus 1. So if we substitute x equals minus 1, yeah, we're going to have to get 0. So 4 times minus 1 to the power of 3 plus minus 1 over 4 to the power of 2 minus 16 minus 1 over 4 plus a equals 0. Yeah, so if we solve all that, we're going to get a. Basically just doing that. So let me just put minus 1 over 4, store it as an answer first. So 4 times answer cubed plus answer squared minus 16 times answer. Yeah, that's 4, so a is minus 4, basically. Yeah, that's it. Because you have 4 on the left side, you gotta solve for a, so you subtract minus 4. Subtract by 4, you get minus 4. Yep. Part B, find the exact y-coordinate of the local maximum. Well, the maximum, we already got x, so we just sub in here to the function, we get the y, right? So we do f minus 1 over 4 here, yeah, to the function. So that's going to be, again, subbing in everything, right? Plus 1/3 minus 1 over 4 to the power of 3 minus 8 minus 1 over 4 to the power of 2. Now we already got the a, so that's minus 4, and then minus 1 over 4 here. And then I'm going to move a little bit to the left for more space. Yeah, plus 17 over 3. Now I got to be careful with what I write here, because it might be wrong. As in if I'm not careful. Yep. Okay, yeah, everything is fine. So I'm going to do the same thing. Do minus 1 over 4 and equal. Store that as an answer again. And then you would have, yeah, I can also look at the screen here. So answer to the power of 4, and then plus 1 over 3 times answer to the power of 3, right? Minus 8 times answer to the power of 2. And wait, this one is minus 4, wait, 4 times answer. Yep. And then plus 17 over 3. Okay. Exact y-coordinate? That's a horrible exact value, right? Don't you think? But we're going to take it. I mean, I'm going to double check it again and see if I made any mistake. Otherwise, I'm just going to take it. So, I mean, if x is minus 4 and a is minus 4 there, minus 1 over 4, I mean, for x, then what could go wrong, right? Because, like, at least we know that a is minus 4 for sure, x is minus 1 over 4 for sure, and we plug in everything. Let me just double check the substitution here. Yeah, I think I'm going to be happy with that. Yep. So we're going to take that, the y-coordinate. Okay, part C. The equation f(x) equals k, where k is a constant, has 4 distinct solutions. Again, this is very similar to paper 1, right? C, using algebra and showing all stages of your working, find the range of values of k. Give the answer using set notation. All right, very similar. Okay, yeah, so let's just draw out, yeah, like that. Okay, and then, well, the line y equals k will be a horizontal line. So if you have that, it's not going to cut 4 points, right? You're going to have to think about the range of places that this line can be placed so that you have 4 intersections with the curve. Okay, so if you place it here, it's 3 points, but we want 4. So you got to go below that point, right? This is 4 now, yeah, you can see. And still 4, 4, 4, 4 until you pass below this point right here. If you pass below this point or at this point, you just cut less than 4. So the upper bound is going to be this, right? And the lower bound will be the other one. Yeah, just these. So you got to be below the upper one and above the lower one. Okay? So yeah, let's just find, so because we already know the upper one here, this is y equals from part B, right? We only need to find that one, right? So to find that one, we're going to have to solve the derivative equation equals 0. Yeah? Yeah, Yeah, we need to find this guy right here. Okay. And we got the derivative equation earlier, this one. Yeah, we're gonna bring that back. So 4x cubed plus x squared minus 16x minus 4 equals 0. Well, we already got one root to be x minus 4. Sorry, x equals minus 1 over 4. So if that is one of the roots, if we make this a factor, then so if say we have 4x plus 1 is a factor of this, of left hand side, right, which is the whole cubic equation there, then we can, yeah, we can do a long division again to get the quadratic factor and solve for the other two, right? Yeah, we can do that. Or we can try factorize it and compare coefficients, so I'm going to do that maybe. So the first one we already know should be x squared, because that's the only combination that you multiply and get that, yeah? So we don't know the second one, we leave it as bx and plus c, so what should be c? Well, c should be 1 times whatever gives minus 4, that should be minus 4, right? So there you go. Okay, so this is just comparing coefficients. And now we got to consider for b thoroughly. So for b, I can look for the x squared term. Let's look for x squared term. So it's going to be 4x times bx, so that's 4b. And then you have 1 times x squared, so plus 1. And those are the only two terms with the x squared, right? This is equal to 1 because that is the x squared term, right? Yeah. So we found that b equals 0. All right. Really? Okay. So if b equals 0, then we have 4x plus 1, x squared minus 4. Let's try check, right? Yeah, that times that, we get that. That times that, we get that. And that's the only one. And then that times that, we get minus 16x. That times that, we get minus 4. Yeah, everything is fine. Yeah, that should be good, I think. So we solve. And that means if we factorize that again, we get x plus 2 and x minus 2 here. That's a difference of squares, yeah? A squared minus b squared can be factorized into a plus b and a minus b like that. So here we're going to pick x equals minus 2 because we know that this local minimum on the left has the x coordinate of minus 2. So we're going to pick that, and then we're going to sub that into the original function to find the y, because don't forget we want the y value. So that's going to be minus 2 to the 4 plus 1/3 minus 2 to the power of 3 minus 8 minus 2 to the power of 2 plus, what was a again? Minus 4, wasn't it? Yep. Let's move to the left. And then x is minus 2 plus 17 over 3, yeah? Okay, so let's plug that in. Again, I'm going to do minus 2 and then answer. So minus 2 to the power of 4 and then plus 1/3 times answer to the power of 3. Yeah, minus 8 times answer to the power of 2. Minus 4 times answer plus 17 over 3. Yeah, everything is okay, right? Let me check. Yep, everything is fine. So that is minus 5. Okay, happy with that. That means in the set notation, right? We have to do in set notation. So k must be greater than minus 5. So we gotta do, is it k, yeah? The set of k where k is greater than minus 5, it can't be minus 5, because if it is, then it will just cut 3 points. And union with set of k where k is less than, what was this one again? It's the fraction, the horrible fraction there. It's 4,735 divided by 768. Yeah, so that would be the answer as in the set notation. Yep, I think I'm happy with that. Reading the question again, yeah, we got everything they need there. So we're gonna do question 9. Okie dokie. Question 9. A new type of car is released for sales. The total number. This type of car sold N in particular region. T months after the cars were released for sale is modeled by the equation. Exponential again. Part A. Find the total number of cars sold in the first 3 months. So basically, just substituting T was 3 in, right? Nothing hard there. So let me zoom in the question again. Yeah. So 5,000 minus 5,000 e to the power of, substituting 3 ins, right? Yeah, 3 T months, yeah. 0.075 times 3. So, it doesn't say whether we should give it how many significant figures. Okay, so let's just do maybe 0.0075 times 3. So maybe I'm gonna give it some significant figures here. Yeah, times e to the power of 0.075 times 3. I'm just checking everything. Yeah, that should be fine. So if we round that, it should be just, okay, let's do 1,007.4189 blah 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 and round that to 1,007 cars, right? That's it. Okay, or you just don't need to write the unit there. Okay, but anyway, part B. Given that n is 3,000 when t equals t, find the value of t giving the answer to 2 decimal places. Nothing hard here, just plug it in, right? Okay, 5,000 minus 5,000 e to the power of minus 0.75 t, and then we solve for t, right? So yeah, it's minus 2,000 divided by minus 5,000 equals e to the minus 0.075 t. Yeah, and then we would have t equal, so that's going to cancel the 2 over 5, right? So we reverse the e, we have ln 2 over 5 here, and then divided by minus 0.075. Yeah, let's do 2 decimal places, of course, as required. So fraction, ln fraction 2 over 5, yep, divided by minus 0.075. Okay, that should be it. So that's 12.2 decimal places, 22, yeah, 12.22. That's going to be capital T here. Yeah, 12.22. That's it. And then part C. Find the rate of increase in the total number of cars sold when t equals 3, giving the answer to 3 significant figures. The rate of increase. So we differentiate. dn by dt equals 5,000 goes away. We have minus 5,000 here. Multiply minus 0.075 e to the power of that t, like that, right? Yeah. And then we want the rate when t equals 3. So dn by dt will just be equal to, so I'm just going to do 5,000 times 0.075. So that's 375 e to the minus 0.075 times 3, right? Yeah. So 375 times e to the power of minus 0.075 times 3. So that's 3 significant figures, so that's 299, right? 3 basic fix. Yep. The rate of increase, so that's cars per month. Yeah, just give it the units as well. Yep. Yeah. Okay, so I'm happy with that. Part D. After a marketing campaign, the total number of cars sold is expected to rise and have an upper limit of that. Using this information, suggest one refinement to the model. So if we take the current model and think about what happens when t tends to infinity, or a very large number, but they say that it's infinity, right? Okay, it's just the extreme end of the real number part. That is not in the real number territory, but it's just some, yeah, infinity, large. Okay, so t tends to infinity, e to the power of minus all that will tend to 0. You just try plug in the calculator, e to the minus 1000, let's say, it's going to be very small already, or it would give you 0 in some calculators. Okay, so that means n will tend to, well, because that is close to 0, so n will be close to 5000. Yeah, minus 0 then. Okay, so it's closing to 5000. Yeah, and have upper limit of that. So we're going to have to adjust, right? Because the current model suggests the upper limit of 5000. Therefore, the refinement is change from 5000 to 65,000. That would have been the case. So if you change that 5,000 to 65,000, so we're going to get n equals like that. Therefore, n equals that. So that's fine. So the whole thing remained the same except this current, the 65,000 there. Yeah? Okay, that's the upper limit. Right. So that's number 9 done. And number 10. Water flows at a constant rate into a large container. There is a tap at the bottom of the container at time t hours after the tap was opened. The volume of water container is V. Water is flowing into the container at the constant rate of that per hour. Water is leaving the container through the tap at the rate of that per hour. All right. Rates of change. Something more fun to do now. Well, yeah, so when you write dV by dt, this is a net rate. You got to consider any inflow or any outflow. In this case, they have both, right? So the inflow will be a positive rate and the outflow will be a negative rate, because the inflow is 0.45 per hour there. Yeah, and the outflow is also minus 0.3 V. So that's it. That's the equation there. We just start from there, and then if we multiply by 20, yeah, because they have a 20 here in front of dV by dt. Yeah, I'm gonna take that. So 20 dV by dt is 20 times that. I think we're gonna get 9 in these, and that's gonna be 6. Yep, as required. Yeah. Given that when the tap was opened, there was a 0.25 cubic meters of the water in the container. So that's like the initial value when t equals 0. We solve the differential equation to show that. Okay, so we're going to solve this differential equation. Well, how about, yeah, so how about doing 20 times 1 over 9 minus 6v dv here on the left. Wait, that's part B, sorry. And 1 dt here on the right. Yeah? Okay, just moving everything there like that. And then we're going to integrate both sides. Yeah? So on this side you have 20, and that is the reverse chain rule for ln x, right? So this is ln of 9 minus 6v. But we have to divide by minus 6, right? So this is dividing by minus 6 there. Just reverse chain rule. Equals, well, this is t, and then you have to plus c, right? Okay. Interesting. Right. Okay. Yeah, we'll get there. So at t equals 0, the volume in cubic meter, yeah, volume is 1 over 4, which is a quarter there. Yep. So we're gonna sub that in. This will simplify to minus 10 over 3 ln 9 minus 6 times a quarter equals 0 plus c. So that's just the value of c that we got, which is minus 10 over 3 ln 9 minus 3 over 2, right? This is 3 over 2. So 9 minus 1.5. So that's 7.5, isn't it? 7.5 is 15 over 2. Yep. I just have to use a calculator anyway, guys. Yeah, there you go. Okay. Yeah, that's equal to c. Okay, can we simplify that? Well, I can make it a positive here. But, you know, just, yeah. So that's my value of c there. And then we're going to plug it back in and prove that it's going to look like that. All right, so let's try that. So minus 10 over 3 here. ln, so let's do 9 minus 6v here already, equals t plus 10 over 3 ln 2 over 15. Okay. Yeah, let's just move them together here, minus 3 over 10. So if you subtract c on this side, yeah, you're gonna have the same coefficient there, 10 over 3 minus, yeah, and both of them will add up, right? Like this. Yeah. And then you can merge them. So if I multiply everything by minus 3 over 10 first, because we have a minus k here. Yeah, so that's going to be a hint there. So I'm going to merge them. 9 minus 6v multiply 2 over 15. Yeah, that's the argument. And that's going to be minus 3 over 10t. I move it on this side because I know that the power of the e here will be a minus something. So I get a minus 3 over 10 there. Because on the next line, I'm going to reverse the ln here to be the e. Interesting, hang on. Oh, yeah, that's fine. So if we multiply inside here as well, we're going to get 18 over 15 on the first term and minus, so 3 can simplify that. Wait, 3 can simplify both, but I'm just going to do 12v over 15 first here. Yep. And this will be e to the power of minus 0.3t. All right. Okay. Yeah, that's fine. So k is 0.3 basically. And then we can, okay, so if we multiply across by 15, yeah, not 15, well, let's cancel first. So 3, 6, 3, 5, 3, 5, 3, 4, right? So I'm going to multiply by 5. I'm going to get 6 minus 4v equals 5 e to the minus 0.3t, okay? And then if I make 4v the subject, I'm going to get 6 minus 5 e to the minus 0.3t, right? Yeah, so that's into places now. And then v would be equal to, p is a positive constant, yeah, 3 over 2. If we divide everything by 4, and this will be 5 over 4. Yep, for the q and e to the minus 0.3t. I think that's it. That's what I got there. Fractions, but okay. Yeah, should be fine. I'm just going to check the math again here. Yep. So minus 10 over 3. Everything move on the same side. I multiply that in. Yep, I think that's okay. Yeah, I think that's fine. Yep. Now part C. Determine whether the container will ever become full. Well, okay, so what's the height of the container? Okay, the capacity of the container is 2 cubic meter. Yeah. Okay. So 2 cubic meters here. All right. So that is probably okay. So if we consider the volume equation here, again, it's just the same method there. We consider when t tends to infinity. Yeah. So again, e to the power of minus kt will tend to 0. So V will tend to P, yeah, because the other term goes to 0. That means P is the upper limit. That means P should be the upper limit, but our P here is actually 3/2, yeah. So volume will approach 3/2 cubic meter. Yeah, 3/2 cubic meter there. But the capacity of the tank is greater than 3/2 is 2, right? Wait, tap remains open and water continues to flow into the tank at the same rate. There is also water leaving, right? Because there is a leakage through the tap. Oh, the tap remains open. Yeah, the tap here is the outflow water. Yeah, the tap. This is the same tap. Water continues. Yeah, all right. So therefore, it's not going to become full. Never become full as 2 is greater than 3/2. That's it. That's the reason, because 2 is the capacity, is greater than the the volume that it approaches, 3/2. All right, and that's it, part C. Number 11. Gonna do here maybe. The company is trying to determine the most profitable selling price for a new toy. Given that if selling price of each toy is £30, the company expects to sell 1,500 toys in 1 year. If the selling price of each toy is £50, the company expects to sell 300 toys in 1 year using linear model, with Y being the expected number of toys sold in 1 year and X pounds being the selling price of the toy. A, find the equation of Y in terms of X, right? It's basically giving you two coordinates in the linear function. So basically you have a 30 and 1,500 and 50 and 300. So the line passes these 2 points. You just have to find the linear model, right? So y minus y1 equals mx minus x1. Yeah, like that. So I'm just going to take this as y1 then. y1 and x1, yeah? So y minus 1,500 equals m. Well, that's going to be 300 minus 1,500 divided by, because we take this as the first one, so it's 50 minus 30 times x minus x1 being 30, right? So that's just the formula there. Yeah, y in terms of x, so we got to push everything to the other side. So what's this gradient here? That's 300, that's minus 1,200 divided by 20, right? So 1,200 divided by 20, that's minus 60, right? Yeah, x minus 30 and plus 1,500. I'm just checking my math. Yeah, that should be fine. And we're going to expand that. So minus 60x plus, well, that's 1,800 plus 1,500. So that's 3,300, right? Yep. And that's the answer to part A. Yeah. Okay. Part B. Show that according to the model, the yearly profit P in thousands of pounds is given by this. In thousands of pounds. Okay. So part B, what do we have? The cost of making each toy is 10. The company has additional cost of that per year. All right. So yeah, right. So we have revenue from the linear model, yeah, which is y here. Y is the linear model. Y is the expected, oh no, hang on. Y is the expected number of toys sold in 1 year. And X is the selling price. Okay, so P is basically cost of making each toy, right? So profit is, right, revenue minus cost, right? That's profit. And revenue is the selling price times X. Wait, hang on, not X, it's Y. Because Y is the number of toys sold in 1 year. Yeah, minus cost. Well, again, the cost is just cost of making each toy. So that's 10y, right? And additional cost of 8,000 per year. So that's minus 8,000. Yeah. Okay, so this is, I'm going to put this as profit first because I remember having read in thousands. So this is not in thousands yet. Yeah, but we're going to do it later. So the selling price is selling price is x, right? Okay, so that's just x times y in terms of x, yeah? So selling price is x, so y is just the whole equation we got earlier, minus 60x plus that, right? And then just going to move everything to the left. Minus 10 times, you know, we can factorize that, so I'm just going to put minus 10 here into the, is that right? No, I can't do that, hang on. Let's just do minus 10 and then y, same thing here. We can deal with that later. And then minus 8,000, like that, all right? So, yeah. And then we simplify this, right? And hopefully we should get what they want there, all right? So expand everything, minus 60x squared plus 33,000x plus 600x minus 330,000. No, it's 33,000. That was 3,300. I read wrong. And minus 8,000 here. Okay, so P is going to be that divided by 1,000. Yeah, because we want in thousands of pounds, right? So that's why the first term we got minus 0.06x squared. Where we simplify the x terms here, we got 3,900, and that is why we got 9.3x. Yep. And then this one would become minus 4,100, which is why we got minus 41,000. That's why we got minus 41 here. And that is as required. Okay, good. Given that the company wishes to make a profit on sales of the toy, C, find the range of possible selling price of the toy. Okay, hang on. Which is to make a profit. To make a profit, we have P greater than 0. Okay? So we want this to be greater than 0, right? So we just set that whole thing greater than 0 to make a profit. Because if it's 0 or negative, that would be no profit or loss, right? Okay, so how do we solve this equation? If let's just, try put that in a calculator and see what happens here. So quadratic. So what was minus 0.06, right? Enter. 3.9, enter. Minus 41, yeah? Enter. Bam. Oh, horrible. Wait, what? Interesting. Okay. Yeah, I'm going to have to write x equals minus b plus or minus square root b squared minus 4 times a times c, like that, yeah, to show the working there, over 2 times a. Yep. Okay. And then we would have the two values being, let's do that in decimal, 51.811, and the other one, what's that? 13.189. Which one is right? Let's see. So, the range of possible selling price. Yeah, that's fine. So we have this. So the range of possible selling price would be, we have a negative parabola here, and so basically it's a negative parabola, and then it's like this. We want the part where the curve is above, so it's going to go like this. Yeah, we want the part where the curve is above 0. So this is y equals 0. So we want this part So it should be in between these two values, right? Yep. So do we have to do set notation again? No. They would really like set notation. So that's the selling price. So we're going to do in selling price X. Yeah, in pounds, right? Yep. Okay. So 51.8. Hang on. I'm going to do that. 51.81 and 13.19. Yeah. That would be the X there. And yeah, and we can't include the two bounds because it would make zero profit, right? Yep. And part D. Hence or otherwise deduce the selling price of the toy that maximizes the profit. Aha. Hence, well, again, this is quadratic, guys. Yeah, and you already have it there. So it's at 13-ish and 51, 52-ish here. So you want to maximize that, and it's a quadratic, so the midpoint is just halfway between 13 and 52. And that is the X value, right? So the X as maximum is just 51.81 plus 13.919 divided by 2 there. That's going to give me, well, I think I can get, oh, that's too late. Hang on. Yeah, let's just do that manually. 51.81 plus 13.19. Yep. Divided by 2. Ah, that's a nice number, 32.5. And then I'm going to store that because I'm going to use it to find the, oh, that's the selling price. So selling price is X, right? So that's it. Yeah, in pounds. 52. All right, so D is done. E. In one particular year, the company sold the toy for £35 and made profit of that. Use this information to evaluate the suitability of the model. Well, basically, I think we just verify the model using X and Y here and plug it in. Note that this has to be in thousands, so that is not in thousands yet. So we got to divide that by 1,000. So we do X equals 35 and P equals 21.75. And we're going to plug that in, see if we get that. So P equals minus 0.06, 35 squared plus 39 times 35 and minus 41. See what we got there. So minus 0.06, right, times 35 squared plus 3.9 times 35 minus 41. We got 22. So 22, well, that's close, right? It's kind of okay, yeah? 22, yeah? And then if we compare the difference, right? So 22 minus 21.75 divided by 22 should be, okay. So we are comparing against the reality there, so we should have 21.75 here down here. And we're going to convert that into a percentage. So that's 20 fraction, 22 minus 21.75 and divided by 21.75, right? 75, yep. Okay, so, and multiply that by 100, we get 1.15%. So I'm going to deem this appropriate because it is only a tiny difference to the reality there. So 21.75. So that profit is only 1.15% different from the estimated P value, estimated profit. Is it profit? Yeah, from the model. Therefore, small difference. Therefore, reliable model. That would be my answer there. I mean, 1% is very close. I mean, if that's the best you can do, it's fine. I mean, you could refine the model further, but it might be worth more to spend time on something else rather than just get the numbers right, right? Yeah. In practice for businesses. All right. Number 12, we have a V-shaped graph. All right. Didn't see that in paper 1 though. Figure 3 shows a sketch of the graph with y equals fx, and yeah, it's the modulus function. Given that a is a constant, and modulus a is 1. So a could be -1 or 1. All right. Find the possible values of fa. Interesting. Okay. So, Okay, so fa could be f1 or f minus 1. All right, so f1 is just going to be 4 modulus 1 minus 3 minus 5. So we're going to get, that's 4 times 2, we get 8, so that's 3. And then 4 of minus 1, right, because a could be 1 or minus 1. And 4 of minus 1 would be 4 times minus 1 minus 3. And everything else the same, so that would be 4 times 4 instead. So that's 16 minus 5 is 11. So that's it. So fa can be 3 or 11. Yeah. The function g is defined by this. Find the range of g of f of x. So we just plug the whole fx into this, the range. Okay, I see. Okay, this is a composite function, so the way I go with this is to find the range of fx first, yeah, and use that as the domain. So we don't need to actually plug in the whole thing. So we find the range of f, yeah, or actually we just write fx, right? So the range of fx here is just anything greater than this minimum point. And that minimum point has a y value of -5, right? So fx greater than -5 here, or equal -5. So that's the range of fx, right? And we're going to use this as the domain for this one. Yeah? Okay? So, I mean, because domain of f can be anything anyway, because x is real number there. But when you consider a composite function, the range of composite function, you got to use the range of the inner part, fx here, to be the domain of the outer part. Yeah, so we consider x greater than -5 on gx, right? So if you plug, this is a linear function, so if x greater than -5, then g of therefore g of fx would be, you plug -5 in here, you're gonna get greater than 2 times -5 plus 17, so g of fx would be greater than 7 there, and that's it. Yeah, that's it. That's the range of g of f of x. Okay, the function h is defined by that equals kx, right? It's a linear function where k is a constant. Given that the equation fx equals hx has no solution, right? Okay. Find the range of value of k, right? So I'm gonna draw it here. Yeah, anyway. Okay, so we have the graph there, and we want hx, which is kx. So kx is basically just a line passing the origin. So we have a fixed point at the origin there that it needs to pass, right? But we have no solution. So let's consider case by case. Note that we have the minimum point here being what? 3 minus 5, right? 3 minus 5. Yeah. So, well, if it's any line that if you draw a simple line to cut, it's going to be like that. But if you want the line that doesn't cut because there is no solution here, so it's going to be maybe something like this. But we want the range of values of k, which is the gradient, right? So the first critical point that this line should be is this. Yeah, and the gradient should look something like that. Let's make that a different color. Yeah, the gradient should look something like that. Yeah, And there is probably another bound if you consider the other bound. So that's where, I mean, let's consider that case first. This is when the gradient is what? Well, it's good that it passes origin, so we can do rise over run here easily to find the gradient of the red line, right? So this is 0, 0 that it passes. That means the gradient here would be m equals, because y is 5, so 5 over 3 minus that. So that's the gradient of that red line. So being the critical case there where it starts cutting the V shape one point. Yeah. So the gradient has to be different from this. If it's greater than this, being like that, greater and greater, it's going to cut the V shape, right? Greater and greater. So it should be less than this, so it goes like that. Yeah, it goes like that. This is less and less. Okay, less and less. It could be this. This is y equals 0. Yeah, no, y equals 0 is this, not that. Yeah, so k can be 0 as well. If k is 0, then we have x equals 0. So x equals 0 is this. Oh, that would cut, right? So if we go, the red line, if we change it to this, it will still, doesn't, no cut there. It won't cut still. But if the gradient changes so that, it's steeper now, they're going to cut here. Yeah, they're going to cut there. So if we keep the gradient, and this is the critical point. So the gradient can't be smaller than this, i.e. it can't go like that. It's got to be like this or less, right? So this is the critical point, and this is the other critical point, right? So this one is when you have, parallel. So this is m equals, the other case is to be parallel with the left wing of the V shape here. This is, so if you multiply the 4 in there, the gradient would be minus 4 because we want the left wing. Yeah, this is either 4x or minus 4x for the V shape. So minus 4 there, yeah, is the other part. Okay, now if we consider the two bounds, we're going to get the range of values of k. Doesn't have to be in Z notation, therefore, so k must be less than minus 5 over 3, but greater than minus 4. Yeah, because if it's less than minus 4, like minus 5, is going to cut the left wing of the V shape. Okay, and that's it probably. Yep. Next, question 13. All right. Given that for all values of k where 0 less than absolute k less than 1, the equation sine in x equals k, right, has exactly 6 solutions in the interval 0 less than x less than 2 pi. I deduce the value of n. Okay, well, let's make it simple first. So if sine x putting to any number, I'm just going to write number so you don't confuse with the k there. So basically, if we imagine, right, a sine graph, in this case, using cast diagram might make it a little confusing, so I'm going to use a graph here. Because you go from 0 to 2 pi, so it's just that, a sine wave, yeah? Pi, 2 pi, because this is a normal sine x, so there is no compressing or stretching. And this is 1, this is minus 1. So the number here can be anything. So if you have y equals some number, it's just going to be a horizontal line there. And you can see that no matter where you go, no matter what number it might be, the maximum answer is 2. So let's say 2, right? Let's say 2. Now, they specify that k is not going to be 0, it's not going to be this, it's not going to be 1 or minus 1, right? Because if it's 1, then this sine x would have one solution. If it's minus 1, it's going to have one solution. But if it's 0, it's going to have 3 solutions. So that bounds there, that inequality here is just helping you so that you always get 2 in one period from 0 to 2 pi. Yeah? Now what happens if you try multiply in x like multiply anything to x here. So let's take it 2 first. If I do sine 2x, now what would have changed? Let's make that green. So sine 2x, right, equals some number now. Yeah, some number. I'm just going to do number here, same thing. Okay. So because you multiply by, and n is a natural number, so it's 2, 1, 2, 3, 4, 5, right? So if you multiply by 2, for example, it's going to squash the x-axis. It's gonna squash the graph or compress the graph along the x-axis. So if you multiply by 2, you're going to shrink this, and the period will get more. So it's going to look like this, yeah? Like that. Now, do you see that for the blue one, you only have 2 points being the intersection, this and this. But when you have the green one, now you have 4 solutions. It is as if just like multiplying the number of solutions by 2 here when you do that, right? And because we have 6 solutions here, now you can see that it should be 3, because I mean, if we draw 3 periods in here, that's going to be tricky for me, but I can try that. 1, hang on. So if it was 3, right, it's going to look like 1, 2, 3, like that, I hope. Yeah, something close to that. Yeah, 3 periods. So 1, 2, 3, 4, 5, 6, right? And the logic is just as explained there. So you're going to have I n equals 6. Wait, no, 3, sorry, because it's in x, yeah? We want sine 3x there, yeah? And I deduce the number of solutions of the equation that, that's now a square of sine in x. Hi guys, just a quick one here. This statistics always blows my mind. So as you can see, for the past 28 days as of today, out of all the 7.7 thousand watch hours, more than 90% of those watch hours come from those of you who aren't subscribed to my channel. And that gives me an urge to beg you, please help support me by subscribing the channel. I will return this huge favor by creating more and more videos. I'm going to utilize my teaching experience for 10 plus years to create the videos covering tips and tricks and the hard bits in the topics that most students struggle to understand. It can either be a short video, a long video, but they will sure come up. So that is why you need to subscribe to stay tuned. I hope we have a deal. Let's get back to the walkthrough. Okay, so let's draw the graph here appropriately since we know it already. It's a sine 3x equals some number k. Okay, so that's sine 3x, right? If we square this, what do we get? So I'm just going to do in red, right? So sine squared 3x. Basically, you just square every y coordinate along the on the curve there. But you see, because we square the value, it's never going to be negative, right? That means we're going to have everything above the x-axis, and 1 is still 1, right? So that's like the cap, and this can never be negative, so it's going to be, and what this does actually is going to double the frequency of, I mean, if I can call this a wave, right? So you're going to have more wave even in here, roughly. You just double. So actually now you would have, rather than 1, 2, 3 waves here, you're going to have 6. So it's going to look like, I hope, like that. 1. Hang on. Yeah, so that's one of them. Yeah. And then you're going to go down here and go up here and go down here and up here and down here and up here and down here and up here and down here. Yep, do you see? Now we have what? And this should be, let me fix that one again. It should be like that, like that, like that. Okay, so if you look carefully here, yeah, I mean, how do I draw this? How do I know? Well, for every 0, you still have 0. See that? For every green zeros here, you still have 0 for the red. For every 1 at the green, you still have a 1. For every minus 1, you put it to 1. Every minus 1, you put it to 1. Minus 1, put it to 1. And it is still a sine wave. Just look like a sine, but it's just shifted up like that. Because don't forget, you can always transform any sine squared or cos squared to a double angle. So it still look like a sine wave anyway, but it's just shifted up. Right? So this is a sine wave, but just shifted up. Now look at this. How many periods do you have? 1. Yeah, gotta be careful. This is starting from the trough there. 1, 2, 3, 4, 5, 6. We have 6 periods compared to before as 3. Right? That means, k squared is going to be on the positive side anyway. So from below, it will go up here, but never greater than 1 anyway. So it's going to look like that. So we're going to have now 12 solutions, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so that's going to be that. So, hang on. So if we are within 2 pi, we're going to cut 12 solutions, but they want 5 pi. Okay, so we're going to go 5 pi, right? All right. So 5 pi, 5 pi is just 2 pi plus 2 pi plus pi, right? Yeah, so the number of solution will be, because for every 2 pi, we have 12 solutions, right? So it's going to be 12 plus 12. And let's see, this is half the period. So half is about, because this is periodic, at the start and at the finish here, we end at the same point, right? It's periodic here. This point and that point is the same point, but on a different period. That means if we do a halfway here, which is the same as that point as well, is in phase, we can work out the number of solution of this half, which is 6, right? So just 1, 2, 3, 4, 5, 6. So that is just plus 6 there for the pi. Yeah? So the number of solution then is equal to 30. 24 plus 6 is 30 there. Okay, and that would be my answer. Justify my answer. Okay, so 12 solutions for every 2 pi, yeah, and I think I showed that in the graph as shown in graph, right there. Yeah, I think I'm okay with that. Just use graphs, guys. Yeah. Okay, so number 14, we're at 1 hour and 20. I did this faster than the other paper, maybe. Number 14, vectors. Something to have fun, I guess. Figure 4 shows a trapezium ABCD. All right, so AD is parallel to DC. Where AD is, okay. Given that AB is that, BC is that, DB is that. This vector question is different from any paper I've seen, at least from my experience. This is going to be good. Part A. Show that K equals 5. Well, usually they just give you the basis vectors like A or B. Like AB might be A, BC might be B. But this one, they give you like all the relative vectors into other forms, and then they ask you to figure out something else, right? So AB is down here, yeah? I'm just gonna, probably I have to use the diagram here. So this is AB. BC is this, right? Yeah? And DB is this, and we asked to show K. Interesting. Okay, and that's 3 marks. Let's see. All right. Yep. So I spotted that because AD was given to be parallel with DC, right? And we can find AD here. So AD would just be basically AB plus BD, right? Yeah, let's find that first, yeah? And I'll tell you what to do next. But I have a plan. So it's just 2A plus 3B plus, well, BD is just minus, it's just the opposite to DB, right? And that would be 4A minus KB, isn't it? Yeah? Yeah, I just multiply by a minus there to DB. So this is going to be 6A plus 3 minus K and B. Just separate that into the I and the J component. Yeah. if you like, just similar to that, but this is an A and a B component. Okay, now this AD, right, is parallel to BC. AD is parallel to BC. That means AD is going to be put equal to some, constant times BC because they're parallel. So AD is a multiple of BC basically. So we can just say that, okay, 6a plus 3 minus kb is going to be equal to some lambda equals BC there. So BC we already know, 15a minus 5b, right? And then we can use something called vector method because these two are, these two vectors are the same. I mean the AD and the lambda BC. So that means we can equate each component separately. I.e. 6a here is going to be put equal to lambda. Sorry, 6, just 6, yeah, for the a component. So we put 6 equals 15 lambda, right? Yeah. So you see we can solve for lambda already. Lambda equals 6 over 15, which is 2 over 3, 2 over 5. Wait, what? 2 over 5, yeah, sorry. And then the b component, right? So we're going to put 3 minus k equals, the b component will be minus 5 lambda. Okay, so k will be 3 plus 5 lambda there. Just solving it, yeah? And then we're going to get k equals 3 plus 5 times 2 over 5, and that happens to be 5 as required. Yeah, happy? Yes. Next. Given also that the point N lies on BC such that BN to NC, BN lies on BC, yeah, somewhere here. Somewhere close to P maybe because it's 1 before that. AN intersects BD at X. Okay, let's draw in the diagram. So my N is around here. AN intersect BD at X. Okay, so we have this line. This is going to be a vector method again. There was one other question in another year, which is also good, going to be similar to this one. I recommend you go check all the hard questions in Pure Math Paper 2 in the video there, and you will see this kind of question. I think it was 2019 or 2020, I don't remember, but go check, yeah. Okay, so, right, so where were we? AN intersects BD at X, so this is X here. And we want to find the ratio of BX to XD. Whatever it asks, it's more convenient to make that some variable and find it, right? So I'm going to let BX to XD equals mu, maybe. Some constant mu, okay? Yeah. So that means... hang on, bx to xd being mu? No. In this case, it's probably less convenient if I do bx to xd being mu. I think the most convenient way is to do bx to bd being mu, yeah, and you will see why. Okay, so bx to bd, yeah, being mu, yeah, I'm just gonna write that. And then what else? Yeah, we already know this ratio, Bn to Nc. So if Bn to Nc is 1 to 4, and Bn to Bc would be then 1 to 5, right? Or 1 over 5. Yep. Why am I doing this? You will see, because we need to find a vector to equate from two different forms. Yeah, we need to find a vector in the two different forms involving two different ratios, put them together, and using a vector method to find the ratios and everything, and prove bx to xd here. All right, so like for example, I mean if I do bx here, hang on. Yeah, all right, so if we directly do bx, right? Okay, so one way to find bx is to directly find it from bd. Yeah, to find it from BD. So BD is BA plus AB, AD, right? So BD we were given, right? We were given BD. So I'm just going to do BX equals, because And that is why I put bx to bd as mu. So I'm going to do mu times bd here. And we already know bd, don't we? bd is just, if you do the minus of this, you're going to have 4a minus kb. So minus 5b, yeah? Because k is 5. And that's bx, one form. We're going to get from a different form involving the other ratio. We're going to utilize this, yeah? So if you walk to bx, you can walk it to bn and nx, right? So I'm going to do bn and nx. See if I have... So we don't know, hang on. Right, we gotta probably make up another ratio here. I'm just gonna do gamma, so I'm just gonna make nx to na, yeah. I'm gonna do nx to na being gamma, yeah, two constants there. We already used lambda up there, so I'm not gonna repeat. So, okay, so bx is bn plus nx, yeah? So it's going to be bn plus nx. We already know bn. Bn will be 1 over 5 of bc. So this is 1 over 5 bc, right? From this ratio, yeah? And bc was what? bc was 15a minus 5b. I just took it from the question here, yeah? And what is nx? Nx, yep, so it's going to be the ratio we made up, which is gamma times the na. And na was just, what is na? Na, don't tell me it's going to involve nb as well. Yeah, na is just, yeah, we can do nb plus ba, yep. Wait, hang on, nx, yep. So nx is gamma times nb plus ba. That's na, right? Yeah. So I'm going to simplify that first. So 3a here minus 1b plus gamma. nb is just the same thing, isn't it? nb, we got it earlier, don't we? Hang on. What's nb again? nb is, oh wait, what? nb. Oh, nb is this guy. Oh, I see. nb is this guy, right? 1 over 5, yeah. So that's going to be 3a minus 5, yeah. It might look weird, but you have the gamma there. Wait, that's bn, not nb. So it's going to be minus 3a plus b, yeah. Because this is basically bn, but we want nb. So I just put a minus sign there and get this. It's basically minus of that, yeah. And, oh, forgot, plus ba. ba was, what was ba? ba was minus of that, so minus 2a minus 3b. Minus 2a minus 3b, yep. Okay, so we're going to simplify all that, right? So here we have a minus 5a. So this is minus 5a minus 2b, right? Yeah. And so we have, for the a component, we have 3 minus 5 gamma times a, because we need to separate into a and b to use the vector method, right? And for the b, right, we have, well, minus 1, right, from here. And then for the gamma, we will have minus 2 gamma times b, right? Just checking here. Yeah, everything should be fine. That's also bx. So you see, you have two different forms of bx involving different parameters and unknowns. And vector method will work here, classic, right? You just have to practice. It's just, so the strategy is to get a vector from two different forms. Bottom line, that's it. Trust me, it works, right? So you got to make up, usually you got to make up two ratios, like I did gamma and mu here in this question, and try to walk on the same vector using different detours, if you like. And then try solve those unknowns, and you're going to get it. So here, because bx equals bx, so I'm going to do look, this one is wait, hang on. Yeah, I'm gonna write that as 4 mu A minus 5 mu B. Yeah, so we have 4 mu for the A on that one equals A on this one. Yeah, vector method. And also the minus 5 mu there is going to be put equal to the B component of that one. Yeah, and that's it. We solve simultaneous. Do you see? Okay, I would prefer to eliminate the mu first, maybe, right? So I multiply this by minus 5. I'm going to get minus 20 mu equals minus 15 plus 75 gamma. Yep. And then I'm going to multiply that by 4. So I get minus 20 mu equals minus 4 minus 8 gamma. And then I'm going to add them up, right? So if I do subtract. Yeah, write them together like this. And then subtract them, just like primary school. You're going to get 0 on this side, and minus 15 minus minus 4 is minus 11. Minus 75 gamma minus minus 8, you get 83 gamma. Ooh. All right. Okay, so gamma is 11 over 83. A bit suspicious there. Right. I'm going to keep going first, right? See what happens if I go with that, yeah? And what do we need? We need bx to xd. Bx to xd, let me just go up. Bx to xd would require that you know, what was it? The mu. Actually, I need to solve for the mu. I eliminated the mu. All right. I should have solved for the mu instead, right? So we're going to use mu equals 3 minus 5 gamma divided by 4 to solve for mu. Yeah. Okay, calculator. 3 minus 555 over 83 divided by 4 in fraction. Ooh, that's horrible, right? Don't you think? Yeah, quite a large number fraction there. As in, the two numbers on the top and bottom are weird. But let's go with that. So that means bx to bd is 97 over 166. Yeah, that's mu. Therefore, bx to xd is going to be 97 to basically just 166 minus 97, right? Because you already got that, so 69. I don't know how they came up with these numbers, but all right. Yeah. Yeah, that's just weird. Okay, I feel like this is weird because bx is greater than xd. Bx greater than xd. Well, that means this is towards that side, which makes it weird now. I need to double check this whole question, I think. I'm going to spend some time. How many questions left? I have 24 minutes left with one question. You know what? I'm just going to spend maybe no longer than 5 minutes. If I see it, then that's bingo. But if I don't, I'm going to skip to the next one. All right. So if I make any mistake here, so let's check from the beginning. I got k equals 5, so that's fine. Then let's check b. So I put bx to bd as mu, yeah, and then nx to na, nx to na, so that's n and x here, and na as gamma, and then bn to bc. I changed that to 1 to 5 because they give you bn to nc. All right, and intersect bd at x. Yep. Find bx to xd. All right, so I said first that bx equals mu bd. That's right. And bd was 4a minus 5b. Is that right? bd is minus of db, so that should be fine. Yeah, and 4 mu a and minus 5 mu b. Okay, this is check. bx is bn plus nx. Yeah, that makes sense looking at the letters. Bn here is 1 over 5. Yeah, 1 over 5 of bc. That should be bc, right? bc, yep, it is bc. So I simplify that to 3 and minus 1. Yeah, that works. And that's bn. And what is this? Gamma. So nx is gamma na. This is na, so it's nb plus ba. Yeah, that's na there. And nb was just found by minusing this whole thing. So nb is just minus of that. It's minus 3a and b. Yeah, that's nb. And ba is this guy. ba is just minus 2a minus 3b. Yeah, that guy. If we simplify this, we get minus 5a minus 2b. Yeah, that's good. I multiply out. So I'm going to get minus 5 gamma a plus 3. So that works for a. And minus 2b, minus 2 gamma b minus 1. Yep. So that's the b there. So I get bx. That should be right. Bx. So bx is that. And now I use vector method to find the mu and the gamma. Maybe it's going to be wrong on this step if it's wrong. So for mu equals the a component, yeah, being that, and minus 5 mu being the b component, being that. Okay, so I multiply this by minus 5, I get minus 20 on that side, minus 15 plus 75, that's right. Oh, I see it. It's 25. Okie dokie, so the simultaneous is wrong. Okay, yeah, I spotted it. Probably do mental math too fast, yeah. You know what? I'm going to change the method. I'm going to solve for mu directly, right? So solving for mu directly, I'm just going to do this equation multiply 2, yeah? So I get 8 mu equals 6 minus 10 gamma. I'm not going to make that same mistake again. 2 multiply, yeah? 8, 6, and minus 10. And this multiply 5, right? So you get minus 25 mu equals, multiply 5, I get minus 5, multiply 5, I get minus 10 gamma here. So that we can subtract the gamma out. So the 8 mu here minus minus 25, I get 33 mu equals 6 minus minus 5, I get 11. Ah, that makes more sense. Mu is 1/3. Nice, right? Nice. Okay, I'm good. Okay, because mu is bx to x to bd. That means if you have bx to bd, b and x and d, 1 over 3, that means xd is 2. Because bx to the whole line, bd, bx to bd, I put that to mu. So that means bx, okay, that's weird. Bx to xd is going to be 1 to 2, yeah? Because bx to bd is 1 over 3, which is 1 to 3, yeah? I write here bx to bd is 1 to 3, yeah? So you get 1 to 2 there for bx to xd. That should be the answer, guys. I spotted my mistake. So, I'm good, I think. As in, mistake-free. Okay, 15. That graph looks nice and it's symmetrical. Figure 5 shows a sketch of part of the curve with equation y equals fx, where if x is that, the curve intersects x-axis at -1 and 1. Alright, as shown. It has a minimum turning points at P and Q. Minimum turning point at P and Q. Alright, as shown in figure 5. A, use calculus to find the exact coordinates of P. So we got to find x and y. Okay, so differentiate, yeah, so f dash x, because we want to find the turning point. Let's see, what should we do? Okay, how about a quotient rule? It's not going to be that horrible, yeah, because we're going to put the derivatives to 0 anyway, so the bottom will go away, but we need to show the working first. So what was it? V du, so v is the bottom one, du, so differentiating 1 minus x squared, we get minus 2x, yeah, the 1 goes away, and minus u dv, right? U, which is just the first bit, dv is differentiating that, so you get 2, bringing the power down first, and power subtract 1, and then do the chain rule inside there, so you get 2x, yeah? So that's the u dv. v du minus u dv divided by v squared, which now becomes to the 4 instead, all right? Okay, so we don't need to worry about simplifying much because we're going to put this to 0 anyway. Yeah, so when this put to 0, because this is a positive number anyway, that means you can just pull that to the other side, multiply 0, and it will go away. So you just have left with, if we factorize minus 2x out, right? And also 1 plus x squared out. Well, let's see, hang on. Oh, you have a lot of, wait. How did I get 1 minus x? Ah, it's there. All right, yeah. Yeah, if we factorize that out, the first term on the top will be 1 plus x squared, the remaining one. And then the other one, with a minus sign there, will be left with still that thing because we didn't factorize that out. And the 2x and that will go away, so we only have the 2 in front there. All right, let me check that. Oh, we should have a plus here because, yeah, we take a minus 2x out. Yeah, I think I'm okay with that because everything is multiplied there. Yep, all right. And we're gonna solve for that, right? I mean, x can be 0. Yeah, that's why you have a turning point up here. This gonna give x solution is 0. You have no solution here anyway because that is not gonna be 0. X squared plus 1 will never be 0. And then the other one possible would be this whole bracket being 0, right? So we're going to equate that. I mean, I don't need the bracket there. So 1 plus x squared plus 2 minus 2x squared equals 0. Yeah? Now the solutions will come from this, yeah? So 3 minus x squared equals 0, sorry. So that means x is plus or minus root 3, just solving that. Okay, so now we know that the p and the q will have minus or plus root 3 as the x coordinate. That means xp will be minus root 3 because it's on the left part of the x-axis there. And we want the y coordinate as well, so yp will be just substituting into fx, which is f minus root 3. That would be equal to 1 minus 3 there, that's root 3 squared, divided by 1 plus 3, yeah, because root 3 plus or minus doesn't matter. When you square it, you get 3 and to the power of 2. So that would become minus 2 over 4 to the power of 2 is 16. So minus 2 over 16, that's minus 1 over 8, right? Yep, okay. So that's yp. That means the coordinates of p would be minus root 3 and minus 1 over 8. That makes sense, yeah? The third quadrant there. Okay, so I'm good with that. D, using substitution x equals tan theta, show that blah, blah, blah. All right, this is very similar structure in compared to the paper 1. They have substitution in the last bit of the question paper. Yeah, so we're going to do dx by d theta first. And that would be differentiating tan is sec squared, right? Yeah. So sec squared theta. Okay, with no chain rule there. And integral minus 1 to 1 fx dx will be now equal to, so 1 minus x squared here, we need to substitute to 1 minus tan squared theta. Because x is tan theta, right? Divided by, again, this is 1 plus tan squared theta. Just put everything into places first. And also squared. And so from this, right, we're going to have dx equals sec squared theta d theta. So I'm just going to put that sec squared theta d theta. Just substituting dx here, yeah? So this This is the whole of x, and this is the dx, yeah? Okay. Well, we got to simplify using some trig identities and cancellation and simplification, of course. Well, I'm not going to worry about the bounds yet. Just simplify this thing first. Oh, we have to worry about the bounds because, yeah. Okay, but simplify first, maybe. Well, because sec squared minus 10 squared is 1, so that means 10 squared plus 1 is sec squared, yeah? So here you have 1 minus 10 squared theta divided by sec squared theta. Yeah, that's 1 plus 10 squared to the power of 2, right? Well, that means it's going to cancel ones, right? Because you have to the power of 4 down here, so you're going to have left 1 minus 10 squared theta over 6 squared theta, d theta. Now, 1 minus 10, that's not going to be 6 squared, right? It's going to be something else. So if we change 10 to sec minus 1, that's going to be 2 sec squared. Okay, I'm going to split that into, let's see. Yeah, so this is 1 minus, because 10 squared is sec minus 1. 6 squared minus 1, right? So I'm going to do 6 squared minus 1 here. I mean, I just feel like doing it because it should be simplified, shouldn't it? So we're going to have here, if you simplify this, you're going to get 1 minus minus 1, so that's 2, right? And then if you split the sec squared there, you're going to get that. And the other one would just become minus 1, right? Yeah, when you like expand all the brackets out. Yep. D theta. So don't you see that this is basically 2 cos squared theta minus 1? And don't you see that that is basically the double angle formula for cos 2 theta? I just felt like doing it, and then I took a leap of faith. Just kept on doing it, and then I got it, right? That's what I did. Now, the bounds. So when x is 1, then theta would be, this is the upper bound. X is 1, well, 10 of pi over 4 is 1, so theta should be pi over 4 in radians, right? Do we do in radians? Yeah, should be in radians because it doesn't tell you the range of x there, so I'm going to say radians, of course. And when x equals minus 1, well, then that should be minus pi over 4. Right, yeah, because it's just a negative of that. Sorry, minus pi over 4. Right? Yeah, I'm just going to take that. And, yep, that's it. Minus 1. Let me think about it. Yeah, that should be fine, right? I mean, it doesn't tell you the range of, yeah. Okay, I'm going to take my chances on that first. So I'm just going to say minus pi over 4 and pi over 4 here. And where a and b, alpha and beta are constant, so it doesn't say. Yeah, so that's fine. That's the answer there. And then let's do part C, and let's see if it works. The finite region R shown in figure 5 is bounded by the y-axis, sorry, the x-axis and the curve, right? So basically now we're going to use that integration from minus 1 to 1. And let's go. So just basically carry on with the integration. So we integrate cos 2 theta, we get sine 2 theta divided by 2, right? Just reverse chain rule. Yep. And then substitute minus pi over 4 and pi over 4 in. Let's see. So sine of pi over 4 times 2, that's going to be sine of pi over 2. So that sine pi over 2 is 1. So that's 1 over 2 minus, that looks good. Sine of minus pi over 2 would be minus 1, right? So that's minus 1 over 2. So minus 1 over 2, so that's going to be 1. All right. Let me double check that. So that would be pi over 4. So that's pi over 2. Sine pi over 2 is 1. So that's 1 over 2. Minus pi over 4 subbing in. So I'm going to get minus pi over 2 there. And sine of minus pi over 2 is minus 1, isn't it? Yeah, minus 1 over 2 here. So yeah, that's right. So the answer is 1. Okay, nice number. And that's it, guys. That's the end of the paper. I have 7 minutes left. I don't think I'm going to spend time doing anything else. And I'm just going to mark the paper and tell you what I got and go through each question and give you feedback and tips. Yeah, so stay tuned. Stop the timer now. All right, guys, I have marked the paper, and as you can see, I got 95 out of 100. And let's see which one I got wrong first before I go through each of the questions and give you feedback on each one and some tips maybe. Yeah, so it's this one. I literally took, in this question, right? Let me just show you in question 6. I think you guys already see it in the walkthrough, right? Because I might annotate it already. So this is supposed to be x over 2. And then I took it as x over 3. So the whole thing collapses here. I don't think I will get method marks here. There would be one method mark and one accuracy mark, because the method mark should be such that I take this as x over 3. But I'm just going to be harsh to myself, so I'm going to take out -2 here. I like 2 marks. But I think this one, yeah, that should be a method mark because I took it from the previous expression there, and I say that this term will be 0, so I just got that. I think I should get 1 mark there. Yeah, so that's first thing. And let's see, this one, yeah, this is question 8. This should be an intersect sign rather than a union. Because it's in the range. Yeah, I got everything correct, but it's just that I need to put in this range. I knew that it was in this range. It's just that I wrote this sign incorrectly. Should have been an intersect, like an inverted U. Yeah. And then which other one? Yeah, this one. Yeah, because in order for this one, this is question 12. In order for this one to have no solutions, right? One of the cases is that the line can be parallel. So it can be -4, because if it is -4, then it's going to look like this, which still with no solution. Yeah. So this should be -4, but it has to be less than this, because if it is this, then it has one solution, which is not what we want. We want no solutions, right? So that has to be an equal sign as well. So I take -1 as well here. And I think that's it. Everything else that I didn't mention was all correct. Yeah, and let's go through all of the questions one by one. Feedback and tips. So overall, I think it's I think it's a well-balanced paper. It's not too easy. It's not hard. I don't think it's hard. It's harder than paper 1, of course, I think. Yeah, and I've heard people say that paper 1 was easy, yeah, in this year. Now, I thought it was also easy, yeah, because I got 100 there. You can check paper 1 there if you like, in the description and in the attached video in the description. And yeah, this one I lost a bit of marks here, but overall, yeah, again, as I said, not too easy, not hard. Yeah, so now let's go through each one. Yeah, like the first few questions are like a warm-up here. I think you guys should be okay, so I'm not gonna go through all of them. Well, this one, right? This one, let's talk about this one. This one, number 3. Yeah, so if you don't know that log property, then you might be in trouble for this one. So the key for this question 3, yeah, is that you know this property very well. Yeah, you can change the log to anything. So let's say if you have log base 4 of 5, you can change it to log base anything. Let's say base 100 of 5 divided by log base, the same base of 4. That also works, right? I mean, if you want to do it. So that means it should also work backwards, i.e. if you have log base something and same base something else, then you can change it to that as well, right? That's a simplified form. Number 4, yeah, this one is fine. Nothing to worry here. I think is if you get the right radian there, you should get the right area at the end, right? So I think that's fine. Number 5, parametric. Yep. So this one might make you a little like unsecure there because the number is too high, but I checked that should be right. Yeah. Yeah, nothing particularly hard here, honestly. Number 6, yep, this one. Well, it's okay. It's just that I made a silly mistake there, I have to admit. But everything else is okay. Although I have to admit that the approximation in the past years compared to this one were actually easier than this. Well, this is like, well, the first one is fine, right? But then the second and the third, it's more like a follow-up question. So, I mean, it's just that there is something more to it than before. Yeah. So before it was kind of easy, just one part of the question and then done. There's no follow-up question like this one. So this is a little more creative than before, but not hard. Yeah, not yet. Right? There are some hard questions. It's not like every question I'm gonna say here is easy. Well, yeah, this one just gotta be thorough with the long division and everything, but otherwise it's okay. This one, right? This one, number 8, we gotta talk about, right? So you get a quartic equation again, quartic function, just like paper 1 you also did. And here you have a quartic where the tricky part, I think, is just the last one. Yeah, well, apart from me getting that wrong, but the last one makes you think about the range of the horizontal line, right? So, yeah, you just have to think about how you get 4 distinct solutions, how you cut 4 times with the curve, right? And the way to do that is to have these 2 lines. And then you have to get the right bounds, yeah? Putting the right set notation in, that was wrong. So I minus 1 there already, yeah? This one should be fine. I think the paper one was harder than this, except this one, yeah? This one, although you could also have 6500 as well, but this is also okay, yeah? And this comes up often now, like the limitation, the tendency, the upper limit. You have seen that many times, so you gotta get used to this one, or at least know how to do it, right? Yeah, exponential modeling here comes up a lot. And yet we have it again here, exponential modeling. This is rates of change actually, yeah, but involving exponential. So you have, yeah, this is incorporating multiple rates in the same question. So you have a positive rate and a negative rate of volume change here. That's why you need to show in part A first. If it was designed to be hard, then they wouldn't have given you this hint. So they would just go straight. Maybe they would combine number 1 and number 2 to be 7 marker here. And then they ask, okay, solve the differential equation to show that V is that, right? Could have been that. Could have been harder if they did that, yeah? And it's in the syllabus. It's within the syllabus. It's not out of the scope here, right? So you need to know that when they give you all the information here, you need to construct the rates of change equation first, and then solve the differential equation. And part C here is like the upper limit again. Yeah. So whenever you have this exponential term, you gotta know that when t tends to infinity, what's gonna happen. I did that many times to show you, right? And that is gonna be very direct work solution there to get the marks, right? Number 10, yeah, some kind of modeling again. This is linear and polynomial modeling. So the first one is linear modeling. You're just gonna have to get the linear function. They both that word, so yeah, you look for that. Yeah, that's great help. So whenever they both some words, you gotta be careful, very careful. Yeah, very careful. All right, so this one, nothing particularly tricky except the thousands here, I would say. Maybe some people lose marks from that. And then B is a great help because you know, in the middle of the question here, if you get anything wrong, if you don't get the same equation, then there would be something wrong, right? Yeah. And yeah, the last part here, compare, right? So if it's within, I don't know, maybe it's within 5%, then it would be also okay. I mean, physically speaking, if you guys do physics, alternative to practical, right? Usually, at least in some syllabus, within 5% difference is considered experimentally accurate. Not sure about mathematical modeling here, but maybe it's less than that. So the acceptable range might be within 2 to 3%. But I would say 5% is still okay. If you deem it worthy, if you deem it accurate by just verifying it because it is within 5%, so that's okay, it's not too great, then yeah, it's just the reasoning is more important than the actual number, if you know what I mean, right? You just have to verify your reason. Yeah. So number 12, this one is interesting. Yeah, this one could be put in paper 1 as well. Yeah, doesn't have to be in this paper, but anyway. So this one is just the hardest part in this question. You just have to figure out the right gradient here. Oh, and yeah, the composite range and domain here. So you should try go back to when I explained that question in the walkthrough, right? Very important. When you have a composite function and you want to find the range of the composite function, you should just, I mean, this is one method which I think more convenient, because sometimes you don't need to get the full composite function expression. I mean, it might be easy, but it's not a guarantee that after you get the expression for the g of f of x here, and it's going to tell you clearly what would be the range. Like I'm saying, if you put the whole fx in the gx here, probably not going to tell you the whole picture either. In this case, it might, but what if it's exponential? What if it's square root? What if it's some more complicated function? The guarantee, however, would be the case when you do this. So you just find the range of the inner function, in this case fx, and make it the domain, the new domain of the outer function, which is the g. So here, this is the range of the inner function. I make it the domain of the outer function gx here. And because if I sub minus 5 into the gx, I get greater than 7. And that is the range, basically. And this is correct. Yeah. All right. So that's it. That's the key part. And yeah, the gradient there, I already corrected it. I think that's fine. 13, this one is a key. It's a key highlight here. This one is, I think, yeah, although the marks are not great, but it's the key highlight here in terms of, you know, how do you know, how do you determine the number of solutions between two functions, and particularly a periodic function like the sine wave here. Yeah, the key part is to know if you square the sine, the period will double, as in you get more frequency of the waves. Yeah, so those of you who do physics might know what I mean here, i.e. you just get more periods in the same interval. So the interval here is 0 to 2 pi. Before you got just 3 periods. When you square, you got 6, right? And then when you draw a line here, you know, it's going to cut 12 times, yeah, per 2 pi. And then we work based on that, we get 30 solutions here. Vector is also a highlight, I would say. This is not easy, I can tell you. This is not easy. I recommend you go check this one again if you don't understand. And also the one that I mentioned in all the hard questions in paper 2. Yeah, if you haven't, just go check them. And yeah, there was a highlight one and the other one as well. So I should put this to the compilation actually. Yeah, this one is also good. Go through that one again if you don't understand. Basically, you find a vector that you can walk on a detour differently and equate them using vector method. That is just the bottom line I tell every student I teach, right? Over and over again. It's just the key strategy there. And the last one is also good. Yeah, this graph here. You integrate, you get the answer. Yeah, nothing particularly hard though. It's just that it is a decent question. Just integration by substitution. You have to show a lot of you have to calculate the exact coordinate of P first, and then part A is not relevant to part B and C though. It's just it's a nice step-by-step question here, and the integration is quite decent. It's just cancel out everything, not too tough, not too easy either, and then get the area, and the area is just 1. All right, just ends nicely there with a very unity number 1. Okay, and that was it, guys. Again, overall paper, not too easy, not hard. That's the bottom line. And if you have watched the video this far, I think you like the video. Why don't you give me a subscribe and please like the video
to support me so I grow my channel more, put more videos like this one. And don't forget to check out other videos, and I'll see you in the next one. Bye.